In this question, we're going to focus on solar power. We're going to look a little bit on how power is calculated, and we'll look at a few of the calculations within it. So, it starts off with figure 5. It shows a graph of current against potential difference for a solar cell when it's a light intensity of 450 watts per meter squared. So we'll start off with determine power output for each solar cell when the input power difference is 5 volts. Use data from figure 5. So the first thing that we're going to have to do is physically go and read off the power output off the graph, right? So we can go and find when the voltage is 0.5, just go read it off, and that gives us 0.91 amps. Right, after that we can simply go and work out the power. So we know that power is equal to voltage times current. We know what the voltage is, we know what the current is. So power must be equal to 0.5 times 0.91, which gives us 0.455. Remember, the unit there is watts. Right, including the unit is really important because it will get you extra marks. The question then moves on to draw a sketch graph on figure 6 to show how the power output of the solar cell varies with potential differences between 0.1 and 0.5. No values needed. Right, remember, if you were only asked to draw a sketch graph, it just needs to be a line showing the direction that, well, the results will take. You don't need to go through and plot loads of different points and point out anomalies and such forth. It's only a sketch graph. So some things on this one in particular that you'll need to note are that it's going to be a straight line with a positive gradient, and it's going to be positive, or there's going to be a positive y-axis intersect. Right. Moving on. So the maximum power output from a solar cell is 0.52 watts. When the light intensity is 450 watts per meter squared, the cell has an efficiency of 0.1 at its maximum power output. Calculate the area of the solar cell. So for this one, the first equation that we need to use is the one for efficiency. So efficiency is our output energy divided by input. We know that the efficiency is 0.15. We know that the output is 0.52. So we can go put that in. So 0.15 is equal to 0.52 divided by our input. So if we go and we rearrange that, we would end up with the input energy working out as 3.47 watts. After we've done that, we need to work out the area. The way that we'll do that is the area is equal to the input energy divided by the total light intensity. We've got the input energy from this first part, so we'll do 3.47 divided by your total light intensity, which is 450, and that will give us 7.7 times by 10 to the power of minus 3. And remember, the unit there, because we're talking about an area, would be meters squared. It's worth taking time on a question like that. Just take your time, go through it a couple of times, check your workings out. So the question finishes with a household has 4 solar cells. Each of the solar cells has a resistance of 0.78 ohms. Explain how the solar cells should be connected so that the total resistance is as low as possible. Right, on a question like this, you've got to think about how they're going to be set up in a circuit. Is the resistance higher in a parallel circuit? Is the resistance higher in a series circuit? So the first thing that you need to talk about is that the cells need setting up in parallel. Then, so that the current has multiple paths that it can take, therefore the total resistance is going to be less than the resistance of one solar cell in series. Right, go back, have another go at this question, take note of the amount of marks that each part of it is worth, and try and squeeze every last mark out of it.